Alrighty, lads and ladies, welcome back to the wonderful world of Calc 2. Today, we are going to learn the last new bit of material for Exam 2. And again, Exam 2 is going to be this Friday during class. I did see that one of you submitted your study guide already. That's awesome. I'll go ahead and give you some feedback for that. I just want to remind everybody else that the sooner you can submit the written work for your study guides, the sooner I can take a look at it and give you some feedback. And that's something that certainly you want to do at least by like Wednesday or Thursday, no later than that, because that's the only way I can give you feedback before the test, and that's really what you want. You will get credit for the study guide even if you submit it like 5 minutes before the test, but I cannot provide you any feedback on your work unless you submit it a day or two before the test. So this, of course, is MAC2312, section number 004, which is Calc 2. And the date today is Pi Day 3/14/22. Like I said, we're going to be discussing today the last bit of new material on the second exam, which is section 11.6 on absolute convergence. And the root and ratio tests. So we're going to have a new definition. That's the absolute convergence part. And then two new tests. There's the root test and the ratio test. These two tests are extremely convenient. You'll love these because they're easy to run. They're very mechanical. There is no you don't need to worry so much about how you structure the logic or what sort of words you use when employing these tests, because they're very straightforward. So you just do a computation, and then based on the value of that computation, you learn whether your series converges or diverges, which is incredibly convenient. Before I introduce the tests, though, I do want to talk a little bit about this notion of absolute convergence. It is a way of further classifying convergent series. So let me give you the definition and we can talk about it a little bit. We say the series sigma an, and this could sum from 0 to infinity or 1 to infinity, wherever, converges absolutely if the new series we get by taking absolute values inside converges. Okay, so that's what it means to say a series converges absolutely. And you see in absolutely the word absolute, and that's referring to the absolute values here, right? You've got an absolute value inside. The thing to think about, right? When you take the absolute value of some number, say, if that number is positive, it stays the same. And if that number is negative, that makes the number positive. So sort of what this series is like if you take the original series, but you force all the terms to be positive. We saw in the week before spring break, when we talked about section 11.5, that, for example, alternating series have a much easier time converging than series of positive terms, like the alternating harmonic series converges, whereas the strictly positive harmonic series diverges. So when you take the absolute value inside, you're making it harder for the series to converge. So this absolute convergence is a stricter requirement than regular convergence. In fact, there's a theorem which says that, although in slightly different words. What the theorem says is if sigma an converges absolutely, then sigma an converges in the normal sense. This could also be said as, well, what does it mean to say sigma an converges absolute? Well, that means sigma absolute value an. I would say sigma absolute value an converging implies sigma an converges. So if you converge absolutely, then you converge in the traditional sense. And again, these series could be summed from 1 or 0, wherever you want, all right, zeros maybe. But remember, when I want to refer to series without worrying about their bounds, when I want to say this is true for series starting anywhere, I'll just write the sigma without the bounds. I will return to that. This will bring you back up to speed with the notation. Okay. There's one more little definition, and then we're going to look at some examples. If the series sigma an converges, but the absolute value series sigma absolute value an diverges, well, that means that the original series is convergent, but not absolutely convergent. If this is the case, then we say that the original series sigma an converges conditionally. So this is as opposed to converging absolutely. So I'll give you a second just to get these things down. Any questions on what's being said here before I start to look at examples and stuff? Okay. One last little metaphor. All series can sort of be sorted into two groups. There are those which are divergent. And then over here, among the convergent series, I can think of this as having two pieces. There are the ones that are absolutely convergent, and the ones that conditionally converge. Right? So if you look at all series, they're either divergent or convergent. And what these definitions and this theorem do is tell us that, well, the convergent series, those can be thought of as having two groups within them. So every convergent series either converges absolutely or converges conditionally. And sort of the new task for us in this section, in addition to applying the tests we're going to learn, is to say whether a series converges absolutely or converges conditionally. Right? We no longer just want to say converges or diverges. No, we want to specify if the series converges, whether the convergence is absolute or conditional. Okay. Let's look at an example. So I have here a task. I'm going to give us some series, and I want to classify each of those series as divergent conditionally convergent or absolutely convergent? And tell me which basket it lives in, and if it lives in the convergent basket, does it live on the absolute side or the conditional side? I'll give us some series to play with here. We can look at sigma n from 1 to infinity, -1 to the n plus 1 divided by n. Sigma n from 1 to infinity, -1 to the n over n squared. And sigma n from 1 to infinity, how about, how about 2 over 3 to the n plus 1? Okay, so quite a bit to do here. If I handed you the series S week before last, before spring break, what convergence test would you want to apply? Yeah, very good. The alternating series test is the way to go here. Because of the -1 to the n plus 1, this series is going to be an alternating series. And if I'm honest, so far, the only test we have for alternating series is the alternating series test. You can use test for divergence if you think the series diverges, but like the comparison tests or integral tests, none of those would apply to this because the terms are not all positive. So I would start by saying S is an alternating series. And we want to write it in the form that makes that alternating series easy to see, right? Where you can tell what the Bn is. So that's, all right, that's -1 to the n plus 1 times 1 over n. So we can say here, the Bn, the non-alternating term, part of our terms, is just 1 over n. And then we run the alternating series test. So remember, I abbreviate alternating series test as AST. Welcome to do that if you want. Just make sure you're remembering the names right. We need to show or check if two things are true. What are the two things we need to check in the alternating series test? Very good. So I need to check that the Bn are decreasing. So the sequence Bn, is that decreasing? And the other thing is that the limit as n goes to infinity of the Bn's is 0. Those are the two sort of questions we need to answer. If the answer to both of those is yes, then we learn that the series S here is convergent. We've done this before. Bn here is 1 over n. So the derivative of the Bn's, Bn primed, would be 1 over n primed. And if you take the derivative of 1 over n, that's the derivative of n to the -1, you get -1 over n squared, which is indeed negative. For all n greater than or equal to 1. So yes, the sequence Bn is decreasing. Check a root there. And then the limit of the Bn's, do it over here, lim n to infinity Bn is when n to infinity 1 over n, which is 1 over infinity, which is 0. So yep, that's a check here as well. Therefore, by AST, the series S equals sigma n from 1 to infinity, negative 1 to the n plus 1 over n, converges. But now that we know about absolute convergence versus conditional convergence, we're not done. There's more to say. I know that the series S is convergent, but I don't know whether it's conditionally convergent or absolutely convergent. In order to figure that out, I need to look at a different series. All right, back at our definition here. The series converges absolutely if the new series you get by taking absolute value inside converges, and converges conditionally if that new series you get by taking absolute value inside diverges. So now that we know he's convergent, we need to figure out whether that convergence is absolute or conditional. So I'll just say absolute or conditional, abs or cond. And the way we do this is just by looking at this new series, where you have the absolute value inside. So sigma n from 1 to infinity, absolute value of negative 1 to the n plus 1 over n. If this series converges, then the original series converges absolutely. If this series diverges, then the original series converges conditionally. So I need to figure out whether this series is convergent or divergent. Now, absolute value, remember, plays nice with multiplication and division, plays nice with powers. So I can say this is the absolute value of negative 1 to the n plus 1 over the absolute value of n, which is just n. And negative 1 to the n plus 1 is either positive 1 or negative 1, depending on what n is. So this numerator here is the absolute value of positive 1 sometimes, and it's the absolute value of negative 1 sometimes. The thing inside here can only ever be positive 1 or negative 1. Both of those numbers have absolute value 1. So this is just sigma 1 over n. This series, does it converge or diverge? Sigma 1 over n diverges. Two ways you could argue that. You could say it's a p series with p equal to 1, which is less than or equal to 1. Or you could just say it's the harmonic series, right? Sigma 1 over n is the harmonic series, and we've shown that to diverge using the integral test in the past. Okay. So the new absolute value series is divergent, but the original series is convergent. So what does that tell me about the series S? That's my original series. Good. On the one hand, we were able to use AST to show that the original series S is convergent, right? Series S converges by AST. On the other hand, when you take absolute values inside, you get the regular harmonic series, which is divergent. So this original series would say is conditionally convergent. And that's the final answer for this first guy. And just a heads up, on your test, I will be asking you for examples of series with certain properties. I might ask you for an example of a conditionally convergent series. You'll see many more in your homework and in the study guide, but this is a good example of a conditionally convergent series. Questions on this work here? Okay, then let's see if we can do the same thing with the series T. The second series we were asked about is that series T. It's the same thing as the last one, but instead of an n downstairs, it's an n squared. So I would start by saying the same. T is an alternating series with Bn here is just 1 over n squared. I can use my alternating series test. I can check that Bn is decreasing. Again, the derivative argument will work here. Bn primed is 1 over n squared primed. The derivative of 1 over n squared is -2 times n to the -3, or -2 over n cubed. And this is negative. Right, the top is negative, the bottom is positive. Well, the bottom has the same sign as n, right? If n is positive, then the bottom is positive, so the whole thing is negative. If n is negative, then the top and bottom are both negative. But here I'm only considering n which are greater than or equal to 1. So this is negative for all n greater than or equal to 1. That is true. So yes, Bn, the sequence Bn is decreasing. The other thing we need to check is the limit as n goes to infinity of Bn. Again, Bn is 1 over n squared, so this is the limit as n goes to infinity of 1 over n squared. That's 1 over infinity squared. Infinity squared is definitely infinity, so this is 1 over infinity, which is 0. So yes, both of these conditions are sound. So T equals sigma n from 1 to infinity, -1 to the n over n squared is convergent by AST. And just like with the previous example, I need to check to see whether that convergence is conditional or absolute. So now that I know the series is convergent, the question is, well, which side of the basket does it live in? The conditional side or the absolute side? And again, the way we do that, the way we always do this, is by looking at the new series you get with absolute values inside. So not the regular series that we were given, but this guy. So we're going to make all the terms positive and ask, is the series still convergent? Last time the answer was no. But this time, when I take those absolute values, I give them to the top and to the bottom separately. N squared again is positive, so certainly the absolute value of n squared is just n squared. Upstairs, the absolute value of -1 to the n, that's still 1. So this is 1 over n squared, which is a convergent p-series. Here, p is equal to 2, which is strictly bigger than 1. Plus my original series t is not only convergent, but is absolutely convergent. Here, insurance companies are evil, evil things. I don't know if I told you guys my car was rear-ended the week before spring break, and I'm just now getting it back. They declared it totaled, even though they valued it at like $10,200, and they estimated the repairs at $8,500. They still declared it totaled, still tried to auction it off, and I had to tell them, no, fuck you, give me my car back, give me some money, I'll fix it. It's been a pain. Anyway, so we found that the series T converges by the alternating series test. That was good news. And then we were able to look at the absolute value series, and that also converged, which means that this original series converges absolutely. And there's nothing wrong with what we did here. I think a lot of people would do this if given this problem. But I want to draw your attention to something. If we had a little bit more foresight, we could have done this much faster. You see, here, we showed that the series, when you take absolute values, converges. Because we had a theorem that said, if you converge absolutely, then you converge, right? If the absolute value version of your series is convergent, then the original series is automatically convergent. So we could have skipped the alternating series test work for this series. Just showing that this guy, the series you get by taking absolute values inside, is convergent would be enough on its own to tell me that the original series converges absolutely. Does that make sense? Do you guys understand what I'm saying there? In other words, we didn't need to do AST for this series. Exactly, Sean. Yeah. So the reason we didn't necessarily need AST for this is because when we look at the absolute value series, he was convergent. So automatically the original series was convergent, right? There's no need to have done the AST. If you can show that a series converges absolutely, then immediately you learn that the series converges full stop. No need for any more detail there. Now, do we know that ahead of time? Not usually, no. But you can start to develop some intuition, right? And the best way to do that is sometimes go ahead and look at the absolute value series first, especially if you think that the series converges absolutely. If for whatever reason, prior experience or the shape of the BN, for whatever reason, you think that your series is absolutely convergent, go ahead and try to show that first. And then if that turns out to be the case, then there's no need to do any alternating series test or other work. Very good. Okay, let's take a look at the last series from this example here, the series R, which was 2 sigma 2 over 3 to the n plus 1. Now, this is not an alternating series. But I can do some algebra with this. That's 2 over 3 times 3 to the n, right? 3 to the n plus 1, that's 3 to the n times 3 to the 1. And that's the same as sigma n from 1 to infinity 2/3 times 1 over 3 to the n. Which is the same as sigma n from 1 to infinity 2/3 times 1/3 to the n. Now, being mindful of what we just said, the little light green note from the last problem, if we think that this series converges absolutely, then we should go ahead and start with the absolute value series. Now, there are other things we can do here. This is actually a geometric series, right? That's what this algebra is showing. This is a geometric series, right? This is sigma, some constant times some other constant to the n. But because I think that this guy is going to converge absolutely, and it's all positive terms, and I'm pretty sure it's a convergent geometric series. So yeah, then I'm going to say, let's look at the absolute value series. Now it's important to note that the absolute value series is not equal to the original series. So you wouldn't put an equal sign between these things. And that's why I'm writing this, to say, okay, we're going to look at another related series instead. Look at the absolute value series. Sigma n from 1 to infinity, absolute value of 2/3 times 1/3 to the n. And generally speaking, this series would be a new series. But in this case, it's not. Because everything in here is positive, right? The absolute value of 2/3 times 1/3 to the n is the same as the original series. Because everything in here is positive. And this is geometric. And the absolute value of the common ratio is the absolute value of 1/3, which is 1/3, which is smaller than 1. So this absolute value series converges. Hence, what can I say about the original series? R. Yeah, perfect, perfect. If the absolute value series is convergent, and here that's true, then the original series not only converges, but converges absolutely. Okay. Do we feel comfortable with the concept of absolute convergence? Fairly straightforward, right? So take absolute values inside your series. If that thing is convergent, then the original series is absolutely convergent. One last little note, and then I'll introduce these new tests. If you take absolute values outside the series, this is not the same as taking absolute values inside the series. So be careful with your notation. Why didn't we talk about this before? Well, before we didn't have the definition of absolute convergence. The reason this is the appropriate place to talk about it is because you need to develop all of these skills with series whose terms are strictly positive, like the comparison test and the integral test, before we can start extending into series where terms are sometimes positive and sometimes negative. So we want to introduce things slowly and give you time to get used to them before we start abstracting. This is kind of one level of abstraction out. Since you asked, well, it's not meant to make people suffer. It's meant to help ensure that you understand. The credo of the math teacher is tell the truth, tell nothing but the truth, but for the love of fucking God, don't tell the whole truth. Because if you dump the whole truth all at once, people get very scared and you know, for good reason, because it's just a lot at once. But since you asked, conditional convergence and absolute convergence are not the only two kinds. There are many, many, many different kinds of convergence. So if following that logic, why not just do it all at once? Well, here are all the different kinds of convergence that exist, right? And you see compact uniform convergence, almost everywhere convergence, LP convergence, convergence in measure, convergence in distribution. There are so many of these things. Even if we're just looking here, right? There's normal convergence, local normal convergence, compact normal convergence, local uniform convergence. There's so different, so many kinds of convergence that I definitely don't want to dump them all on you at once. Real quick, before we finish this, I said these two are generally not equal, right? Most of the time, these are not the same thing. And there are some series where those are the same, but most of the time they're not. However, there is a statement like this, which is true. This is sometimes called the triangle inequality. It's actually a sort of infinite version of the triangle inequality, which says that if you take the absolute value on the outside of your series, you will always get something that is less than or equal to the absolute value inside the series. And the key to proving that theorem that I claimed at the very start of class, that if you converge absolutely, you converge in the traditional sense, is this triangle inequality, right? Because if this thing is finite, that means this thing is finite. But if the absolute value of your series is finite, then your series itself must be finite. This is actually a pretty deep statement that we care about a lot in a slightly more grown-up math class. If this were a real analysis class, we would be using this fact like 10 times a day. Okay. So, absolute convergence, conditional convergence. Why is today the day to introduce these things? Because the two new tests that we're going to learn today have as their like good case output, when the test succeeds, they tell you not only that the series converges, but that the series converges absolutely. So let me show you the root test first. And I'll give you a little proof of the root test, and then I'll show you some examples, and then I'll show you the ratio test and some examples. This says, given a series S equals sigma an. Could be summed from 1 to infinity or from 0 to infinity. I don't care. Maybe all. Given a series S equals sigma an, calculate this number, we'll call it L, as the limit as n goes to infinity of the nth root of the absolute value of an. Just drifted out of focus quite a bit. So I don't care if this is a series with positive terms or some terms positive, some terms negative, alternating series of grandmas, whatever. Given any series S, you can calculate this limit. And then if L is smaller than 1, that tells you that the series S not only converges, but converges absolutely. This is nice. If L is bigger than 1, then the series S diverges. And there is no qualifier for diverges, right? You don't say diverges conditionally or diverges absolutely. It's just converges absolutely, converges conditionally, diverges. And then the missing case here, if L is equal to 1, the test is inconclusive. And there are a lot of series where this test is inconclusive. There are a lot of convergent series where this test is inconclusive. There are a lot of divergent series where this test is inconclusive. Right? There are many absolutely convergent series where this test is inconclusive. So while this test is very easy to use, it is not all-encompassing. It's not like this test works on everything, but it does work on a lot of stuff. I want to sketch for you a quick proof. And I'm just going to handle the first case here. Suppose S equals sigma an and L is less than 1. Where L is the limit as n goes to infinity of the nth root of the absolute value of an. What this means is that L is approximately equal to the nth root of the absolute value of an for large values of n. Right? And this is something we've talked about before. Yeah, if you have the limit of some stuff going to 5, that means that stuff gets closer and closer and closer to 5. So for very, very big values of n, that stuff, whatever it is, should be close to 5. So if I tell you that the limit as n goes to infinity of the nth root of an is L, that means that the nth root of an is very close to L for large values of n. That means this thing gets closer and closer and closer to L. Raise both sides here to the nth power. And you get that L to the n is approximately a sigma absolute value of an. And if you then sum, you get that sigma L to the n is approximately sigma absolute value of an. On the right-hand side down here, you have sigma absolute value an. That's the corresponding absolute value series for my original series S. On the left-hand side, you have sigma L to the n. And since we assumed that L was less than 1, this geometric series, right, sigma L to the n, that's a geometric series. This geometric series must converge. L is, of course, positive, right, because it's you could never get a negative thing out from this limit, right, because the first step is take absolute values, then take the nth root, then take the limit. So if L is less than 1, then its absolute value is automatically less than 1. And that means that the geometric series sigma L to the n must converge. Therefore, sigma absolute value an. If this series is basically the same as this series, and this series converges, then this series converges. But by definition, that means that the original series S, just sigma an, converges absolutely. All right, that's it. That's it. So what we were trying to prove is that if L is less than 1, where L is that limit, if this number is less than 1, then the series sigma an converges absolutely. That's what the test says. And we're able to show that if you have a series S equals sigma an and L is less than 1 for that series where L is this limit, then that series should converge absolutely. And that's precisely what we were able to show. You can also see here how if I assumed L was bigger than 1, when you get down to this stage, you'd say, oh, well, then this geometric series diverges because its common ratio is bigger than 1. And since that divergent series is basically the same as my absolute value series, my series must also diverge. Or at the very least, can't converge absolutely. But I just wanted to prove for you this one part of the theorem because I think it's enlightening. The thing I'd like you to take away from this proof is that the number L from the root test is similar to a common ratio for our series S equals sigma an, even if S is not geometric. So this number L that you calculate as a part of the root test is finding like the closest geometric series to your series. Maybe your series is or is not geometric. If you apply the root test to it, that will tell you like if your series was a geometric series, here's what the common ratio would be. In other words, it's almost like a comparison. You're almost comparing this to a geometric series. It says your series, whatever crazy bullshit that is, here's the geometric series that is most similar to your series. And definitely if you apply the root test to any geometric series, it will give you the common ratio for that series. All right, let me show you through an example, concretely what I mean here. So I'm just going to say investigate. And by investigate, what I mean is converges absolutely, converges conditionally, or diverges. How about 2 to the n divided by n times 5 to the n? So a quick comment, this series is not geometric. If it was just 2 to the n over 5 to the n, that would be geometric, but this n throws off the geometricness, right? That's sort of what I'm trying to get at with that comment. So while this series is not geometric, it is kind of similar to the 2 to the n over 5 to the n series. Upstairs, 2 to the n is the only thing. Downstairs, you have n times 5 to the n. Both n and 5 to the n grow as n grows, but 5 to the n grows much, much, much faster. So much faster that this n almost kind of doesn't matter. I mean, it's there, but what we're going to see is that this thing shares its convergence behavior with the geometric series 2/5 to the n, sigma 2/5 to the n. Now, as always, you're going to tell your reader what test you're using. Always tell your reader what test you're using. So when you go on the exam and you're starting to fill out your solutions, make sure that as you answer those questions, you tell me what test you're doing. And then another little pro tip, always tell me what you're trying to calculate before you calculate it. Because if you make a mistake, I can still give you some credit if you show me that you know what you're supposed to be doing. So the root test says calculate L as the limit n goes to infinity of the nth root of the absolute value of an. Here, that's the limit of n goes to infinity of the nth root of 2 to the n divided by n times 5 to the n, and then there's absolute values inside the nth root. Now, thankfully, 2 to the n is positive, n is positive, 5, oh, sorry, this is 5 to the n. It doesn't look like it does it. 5 to the n. Everything here is positive, so the absolute values just go away. And we get the nth root of 2 to the n divided by n times 5 to the n. And you can give that nth root to each of those pieces separately. You got to remember your rules for exponents, your algebra. So this is the nth root of 2 to the n divided by the nth root of n times the nth root of 5 to the n. We'll continue this up here. This is equal to limit as n goes to infinity. What is the nth root of 2 to the n? Good, just 2. The nth root of n I'll leave alone for now. He's a little bit scary. The nth root of 5 to the n, same as the nth root of 2 to the n is just 2. The nth root of 5 to the n is just 5. So there's a factor of 2/5 here that I can bring out of the limit. We get 2/5 times the limit as n goes to infinity, 1 over the nth root of n. I'm going to leave some space here because this limit, this is actually kind of tricky. So down here, I'd like to ask you, what is the limit as n goes to infinity of just the nth root of n? What is that equal to? It's an interesting question. So it's not immediately obvious, right? Let's let an be the nth root of n. The nth root of n, another way you can write that is as n to the 1 over nth power, right? Remember, an nth root is the same as the 1 over n power. And observe that the limit as n goes to infinity of an here would be the limit as n goes to infinity of n to the 1 over n. The power there, 1 over n goes to 0, right? 1 over n on its own goes to 0, but the base n is going to infinity. So this is like infinity to the 0. And that's a problem. Right? Remember, infinity to the 0 is an indeterminate power. Now, I don't want to spend too much class time on this because this is something from 11.1. It's something that we've technically seen before. So to handle this, this requires working with the natural log of n, which would be 1 over n times the natural log of n, and using L'Hopital's rule. Again, I'm not going to go through the details here. We did do a few of these indeterminate powers in class back in 11.1. The result is that the limit as n goes to infinity of the nth root of n, which you could also write as limit n to infinity n to the 1 over n. If you encounter either of these expressions, you're going to get 1. And I don't recommend going through the L'Hopital's rule stuff every time you see this. I would remember it so you can use it freely. This is something I will allow you to use on the test without showing work. You need to get something into this form, but when you see an nth root of n and you're taking the limit as n goes to infinity, you can just tell me that that is 1. That is okay. So with that in our pocket, we come back to our problem and we see that this is 2/5 times 1/1, because that nth root of n goes to 1. So this is just 2/5. So L from the root test here is 2/5, which is less than 1. The series S equals sigma n from 1 to infinity, 2 to the n over n times 5 to the n, not only converges, but converges absolutely by the root test. And you want to tell me that it converges absolutely. You want to give me all that information. Okay. So again, special limit here, something you want to tuck in your little memory box or make a flashcard for. Yeah, the other kind of special limit like this is the limit as n goes to infinity. I call it the e to the ab limit, 1 plus a over n, all raised to the power of bn. As n goes to infinity, this is e to the ab. And those are two limits that I would recommend having ready to use without needing to go through the work. Okay, only a few minutes left. I want to show you the ratio test. The ratio test is very similar to the root test in that it does that same thing. It finds the most similar geometric series, or really it finds the common ratio for the series, the geometric series that is most similar to ours, right? I said this n kind of doesn't matter, right? That it's really the 2 to the n that's in charge upstairs and the 5 to the n that's in charge downstairs. If you covered up this n, then this would be sigma 2/5 to the n, which is a geometric series with common ratio 2/5. Well, shit, that's what we got out from the root test. L was 2/5. That's what I meant when I said that. The ratio test does the same thing, but instead of taking an nth root of the nth term, it takes a ratio of consecutive terms, which is more in line with how we defined the common ratio. So this is called the ratio test. And it says, given S equals sigma an, calculate L as the limit n goes to infinity, absolute value of an plus 1 over an. I'm not too familiar. So there's a question here I just got. How do I feel about the personal study plan within WebAssign? I'm not too familiar with it. I know that Cengage and WebAssign are working on some artificial intelligence that's supposed to sort of help you, like by selecting problems that maybe you got wrong the first few times and putting together a set of problems like that. But I don't have any personal experience with it. So if you're playing with the personal study plan, I think that's probably a good idea. Let me know what you think. Let me know what you think about the personal study plan there and tell me how it's working for you, because I'd love some feedback, but I don't have any direct experience myself. All right, so ratio test says, given a series, any old series, doesn't matter, calculate, we're still going to call it L, just like with the root test, but this time it's the limit as n goes to infinity, absolute value of an plus 1 over an. And then everything else is the same. If L is less than 1, then the series S converges absolutely. If L is bigger than 1, then the series S diverges. And if L is equal to 1, then the test is inconclusive. I'm not going to go through a proof of the ratio test. It's similar to the proof of the root test. It's not going to teach us anything special or magical. I do want to make one note here, and that is if the root test is inconclusive on a series, then so will be the ratio test. And vice versa. So if you get the inconclusive result here, if L comes out to 1 for you using one of these tests, don't try the other. In fact, L should come out the same for pretty much all series, whether you're using the ratio test or the root test. It's just that sometimes the algebra is easier with one than with the other. Here's an example. Let's investigate the series S equals sigma n from 0 to infinity n plus 1 over n factorial. Yes, correct. First thing here says if the root test is inconclusive, then so will be the ratio test, and vice versa. So this is root test, this is ratio test. In other words, the two tests fail on the same series. All right, I would say that L coming out to 1, this being inconclusive, means the test has failed me. It's not giving me a definite answer. So the two tests, the ratio test and the root test, they fail on the same series. A fun problem is to figure out what series the test fails on. And I'll give you a hint. Any ratio of polynomials, when you plug that into the root test or ratio test, you should get a lot of cancellation. Okay. I'm going to use the ratio test on this guy. And the hint, anytime you see factorials or factorial like products, that's a strong hint to use the ratio test, because those things cancel very nicely. Right, we saw back in the 11.1 homework that you can cancel fractions with factorials very, very nicely. So we tell our reader what we're doing. We're going to use the ratio test. Okay. The ratio test says compute this number L. It's going to be the limit as n goes to infinity, absolute value of an plus 1 divided by an. And we go ahead and do the computation. So you need to be a little bit careful about figuring out what an plus 1 is. Notice this plus 1 is in the subscript. So it's not like I'm just going to take this thing and add 1. It means I'm going to replace n by n plus 1. So an plus 1 is n plus 1 divided by n plus 1 factorial. And then I need to divide this whole thing. Let me extend this down a little bit. I need to divide this whole thing by regular old an. And an is n plus 1 over n factorial. So here is the thing I get from the ratio test. And I know it looks scary, but trust me, it's not. And you practice a little bit and it gets very simple. Let's clean this up a little bit. N plus 1, that's n plus 2. Downstairs here, I have still n plus 1, all parentheses factorial. The parentheses really matter there. Don't skip them. Still have my absolute values. And then dividing this whole thing by n plus 1 over n factorial, that's the same as multiplying by n factorial over n plus 1. This is a 2. The trick with the ratio test limits is to group similar pieces together. So like I've got a factorial here and a factorial here. This is all being multiplied. These are just fractions multiplying, they multiply straight across. So what I'm going to do is I'm going to put the factorials together. Right, multiplication is commutative, so n plus 2 times n factorial is the same as n factorial times n plus 2. I can shuffle them around like that. And then down here, I have my n plus 1 factorial. And over here, I have my n plus 1. I'm getting rid of the absolute values at this step also, because everything inside here is positive. I'm sending n to positive infinity. Definitely the factorials only ever spit out positive numbers. N plus 2 and n plus 1 are both going to be positive. So the absolute values I can get rid of at this step, but make sure you include them at the start because you can't always get rid of them. A lot of times there are negative things in here. So continuing within the algebra. I need to simplify n factorial over n plus 1 factorial. And the trick to simplifying factorials is to just write them out. N factorial is n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. Right? Anything factorial is that thing times that thing minus 1 times that thing minus 2, all the way down until you get to 1. It's what you get when you multiply all the numbers that are less than or equal to the thing being factorial. So applying that same logic to n plus 1 factorial, n plus 1 factorial must be n plus 1 times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. And then I still have the other piece over here. I have n plus 2 over n plus 1. So this is my limit. And there is lots and lots of cancellation. So the n's cancel. The n minus 1's cancel. The n minus 2's cancel. Everything cancels, except for this n plus 1. So I get limit n to infinity 1 over n plus 1 times n plus 2 over n plus 1. Let's just look at those pieces separately. What does n plus 2 over n plus 1 go to as n goes to infinity? Well, it's true that if you just plug in infinity, you get infinity over infinity. But we've seen lots and lots and lots of limits like this. right, where the top and bottom are both just like polynomials. So yeah, it's correct to say that if you just plug in infinities, you would get infinity over infinity, and that is indeterminate. But in this specific case, this piece is going to go to 1. Right? The degree of the top is 1, the degree of the bottom is 1, and the ratio of lead coefficients here is 1 over 1. You could apply L'Hopital's rule just to that piece if you want, or you could divide top and bottom by n if you want. But we want to be to a place where we can take these sort of limits quickly. This piece, 1 over n plus 1, this is going to be 1 over infinity. That's going to go to 0. So what we get out of this is 0 times 1, which is 0. So L here is 0, which is indeed less than 1, which means our series S equals sigma n plus 1 over n factorial summed from 0 to infinity converges absolutely by the ratio test. Questions on this one? Okay, we have time for one more here. Let's investigate the series S equals sigma n from 1 to infinity. How about n to the n times 2 to the n over n factorial times 3 to the n? This is pretty nasty. Now you've got this 2 to the n over 3 to the n here. If you only had that, then this would be a geometric series, but we've also got this n to the n and n factorial, both of which are pretty wonky. The n factorial here hints that we should use the ratio test. Although you could also try the root test. Having a bunch of stuff raised to the n is usually a good hint for the root test. I think the ratio test will be easier here, although both are quite bad. L is going to be the limit as n goes to infinity, absolute value of an plus 1 over an. And I'll jump straight to the step where you multiply by the reciprocal of an. So we'll have the absolute value of, well, let's see, what is an plus 1? That's n plus 1 raised to the power of n plus 1 times 2 to the n plus 1 divided by parentheses n plus 1 factorial times 3 to the n plus 1. This is an plus 1. And we need to multiply this by the reciprocal of an. We're going to flip over an. So instead of writing a big fraction and divided by, I'm just going to flip and multiply here. So I've got my n factorial times 3 to the n over n to the n times 2 to the n. There's my ratio test limit. Lots of different pieces. But remember what we said on the last problem. We should just group the like pieces together. Everything here is being multiplied. So I'll put the factorials together. There's an n factorial upstairs and n plus 1 factorial downstairs. That's n factorial over n plus 1 factorial. There's an n plus 1 to the n plus 1 upstairs. And an n to the n downstairs. Those are the two sort of super exponential pieces. And then there's 2 to the n plus 1 divided by 2 to the n, and 3 to the n divided by 3 to the n plus 1. All of this is in absolute values. Forget about the limit for a second. What is 2 to the n plus 1 over 2 to the n? What is this fraction? Good. This is just 2. All right, just a little bit of algebra. What about 3 to the n over 3 to the n plus 1? What if there's one extra 3 downstairs? Very good. That's 1/3. So there's a 2 times 1/3. That's 2/3. That can come all the way out of my limit. Let's pull him out. Everything here is positive, so I can get rid of the absolute values at this stage also. And I have just the n factorial over n plus 1 factorial times n plus 1 to the n plus 1 divided by n to the n left. And this limit is not an easy limit. But I'll walk you through it. And there are other similar limits that you're going to have to work through in the homework and potentially on the test. So pay careful attention to what we do here. In the last problem, we canceled n factorial over n plus 1 factorial. We saw that that's just 1 over n plus 1. And then n plus 1 to the n plus 1 is n plus 1 to the n times n plus 1 to the 1. And you can cancel these n plus 1. So that leaves you with n plus 1 to the n divided by n to the n with a 2/3 output. And even this limit is a little bit tricky. It's not obvious what this is going to come out to. N to the n on its own goes to infinity, gets there super fast. N plus 1 to the n also goes to infinity, also gets there super fast. And if you tried to L'Hopital this, you're going to have a problem because differentiating n to the n, that's not easy. This requires logarithmic differentiation, which you may or may not remember from Calc 1. I would guess most of us don't. But L'Hopital's rule isn't what we're going to do here. This is going to turn into one of my special e to the ab limits, because I can rewrite n plus 1 to the n over n to the n as n plus 1 over n all to the n. See that, right? If I've got a fraction and the whole top is raised to the n, the whole bottom is raised to the n, that's the same as having that fraction with the whole thing raised to the n. And that's what we've done from here to here. Now just one tiny more bit of algebra, n plus 1 over n. That's n over n, which is 1, plus 1 over n, all to the n. I'm doing here saying that n plus 1 over n, all to the n, is n over n plus 1 over n to the n, which is 1 plus 1 over n to the n. That's the algebra there. And that limit is e. Right? This is e to the 1 times 1. So I get 2/3 times e. And the question is that bigger or smaller than 1? Well, e is like 2.7. So 2 times 2.7, right? This is about 2 times 2.7 divided by 3. Right, 2.7 times 2 is 5.14. And this is definitely bigger than 1. So the series S equals sigma n from 1 to infinity, n to the n times 2 to the n over n factorial times 3 to the n diverges by the ratio test. So those strange limits from section 11.1, the reason we covered those back then is because they show up here. Yes, they're interesting on their own, but we need them here as well. And so you might want to refresh yourself, especially as you study for this test. Make sure that your limit skills are good, right? If there's one like core mathematical skill that comes back over and over and over again through this section, it's limits, right? And there's lots of algebra notation, lots of logic and language. But the core mathematical skill that we're relying on here is taking limits at infinity. So you got to practice those until you're really, really comfortable with them. The study guide has been open since last Monday. It's been open for a week today. If you haven't started on that, please start on that as soon as you can. The sooner you can turn your work in on Canvas, the sooner I can give you some feedback on it. And that feedback is generally very helpful in preparing for the test. So I want to encourage you to turn in that study guide work as quickly as you can. If you've already submitted it, I'll be going through this afternoon and taking a look and entering some feedback, and then I'll keep a steady watch on it until Thursday afternoon. If you can get it in before Thursday afternoon, I'll be able to get you some feedback before the test. Yeah, happy to extend anything you need extended. Just go ahead and put in a request. I did clear extension requests on the first day of spring break, and then I've cleared them again this morning. So if you had an extension request in that you put in over break, it should be cleared by now. But if you do need something extended, go ahead and file an extension request, and I'll be taking a look at those during my office hours today. Any other questions before we wrap up here? Okay, then, just a reminder, your test is on Friday. It's during class time, and it will cover everything from 7.8 through 11.6. Wednesday, we'll be doing a review day. So please bring problems that you want to see discussed or worked on. It can be problems from the study guide. I would prefer problems from the homework. If there's a study guide problem you really want to see, then I can solve a similar one. But look back through the homeworks, look through the study guide, see if there's anything that you want to see talked about or worked through in class on Wednesday as a part of your review. And the test then will be on Friday. That is it from me. Oh, sections 7.8 through 11.6. There's 11.7 stuff in your study guide. 11.7 doesn't have any new material. It's just like strategies for testing series. So the sections you need to make sure you're comfortable with are 7.8, 11.1, 11.2, 11.3, 11.4, 11.5, and 11.6. 7 sections from 7.8 to 11.6. And then if you're looking for extra problems to practice, go to 11.7 in the textbook. Okay, gang, I'm going to go ahead and end the meeting here. I hope you guys had a lovely break. Welcome back. Let's go ahead and get ready for this test, and then I'll see you on Wednesday. Take care.